Howdy.
Hey guys, how are you doing?
Good, thanks. This actually collides with an IEEE mixed signal
Yeah.
committee meeting, so I'll probably sit in on this since it's on a different meeting thing. But I'll be silent and well, I'll maybe sort of try and seg out and back in later.
Sure. Apologies about. Hey Dan, apologies for the time. I think it's the best we could find. We can maybe discuss it more. But there's a recording, so you can probably watch it afterwards, but you won't be able to ask questions. And you can send an email to Dan. I'm sure he can answer some of it.
It's an IEEE meeting, so it's like it'll wander about. I may be able to get away from it.
Where does the large QR code over the I shot there lead?
I think it's my website. I'd have to check it. I got a bunch of QR codes. I'll just switch to the webcam. But, yeah.
So you may feel like a dork holding your phone up to your computer to get a QR code URL, but you'll have plenty of opportunity to do that during this talk.
Yeah. Oh,
that's actually a very.
I
was going to say that's actually a very effective technique.
I don't know. It's like
I'm not sure if it is, but we're going to try it.
Yeah.
No, I actually on my television set here, when I sign up for like some streaming service like Disney Plus as an example, I'll just use that, but like it will flash the QR code up on the TV and it magically picks it up from what I've already done on the web. So it works great.
I think for stuff like this, it's probably more effective in a big conference room, like in a hall at ISCCC or something than it is in this kind of forum, where people really don't have access to. People really just have like 100 foot away, big screen in front of them. But hopefully it's helpful.
Unreal.
Mehdi, I added those folks for you, so hopefully that worked out okay.
Yeah, thanks, Rob. How did the GSC meeting go? Sorry, I couldn't attend.
Oh, it went well. It was only half hour long, but I think it got the necessary tasks done. So it was a good meeting, actually.
Great. Yeah, and Dan, really sorry about last week. I was got really high fever and I just couldn't make it.
No problem.
Yeah.
You feeling all right?
Yeah, feeling much better. So have you designed a SerDes design now, or is that is it a test chip?
So that'll be a good chunk of the talk. In progress test chip. That's where a lot of my background is, and that sort of intersects with a couple of other threads going on here. So we thought that would be a good combo project for a lot of the software I'm going to show the next hour and the open source PDK and the backgrounds of some of the folks we have available here.
Sure. So I invited Anhang and a postdoc from our group because they're working on SerDes, and I was hoping they can see a bit of your work, I guess. So we're pretty excited about it.
Do you pay attention to the OCP BOW stuff at all?
Not really.
Okay, it's another SerDes thing.
Oh, okay. Do you mind sharing a link or something we can take a look?
I'll try and do that. It's an open compute project. It's just one of the many sub projects. A bunch of wires. They've been working on a SerDes thing for the last couple of years at least.
Oh wow. Okay.
Blue Cheetah is the company sort of driving that.
Oh yeah.
San Francisco.
Yep.
I'll try and be back.
So let's wait a couple of minutes. Maybe we'll get more people. Sure.
Yeah, sure. Just let me know.
All right. Well, okay. I see a couple other people just joined, so that's good. Cool. So thanks everyone for joining. First, I would like to apologize for last week. I was having some health issues. I'm feeling much better right now, and I'm really excited about the talk from Dan Fritchman from UC Berkeley, who will present the design of an open source USB PHY using a couple of tools. One of them is the Python-based analog HDL, which I'm pretty interested in, and it's paired with the schematic system. So I'm looking forward to hearing more details about that. And he's using a couple other tools like VLSI-R and layout programming with layout 21, GTS 21, and Left 21. So Dan Fritchman, please share your screen and tell us more about your work.
Yeah, thanks, Mehdi. And just to maybe correct, just to maybe set expectations a little bit, we are going to focus a bit more on the latter half of what you just said. So all of the software behind this. Is the presentation coming through?
Yep.
Okay, great. So I'm going to talk about a long list of stuff. Mehdi just rattled off. In fact, we're probably not going to cover all this. We're going to get probably 3/4 of it in an hour. First, I think it's worth introducing me, where I'm coming to this from. I don't think we know each other all that well in the group. I've been at Berkeley for just about 3 years now. I had a good stint in industry in a couple of different capacities before that. I started as a system designer, did a bunch of embedded systems, but spent really the bulk of my career to date as an analog IP designer, as an analog circuit designer, primarily at Apple and primarily for the analog and mixed signal circuits in the SoCs. And in the more recent years, both late term there and here at Berkeley have been more in the software, therefore. So I come to this from the perspective of analog designer, and that'll motivate a lot of the stuff we'll look at. And you're probably thinking that given we have a talk with analog in the title and a speaker with Berkeley in the bio, that we're going to talk about a project you've probably heard of called BAG. And we're really not. Other than as an initial sort of cautionary tale. In a brief historical view of that project that motivates some of our work. That history, I think of in a few eras. So kind of prehistory, in a sense, is the circuit researchers here at Berkeley do it like everybody else. Click around, cadences virtuoso, draw schematics, draw layouts and such. And eventually some smart grad students and professors realize we do a lot of this similar stuff over and over again. It is amenable to being programmed. We have programs that figure out how to design these circuits at higher levels and put together BAG, which is in a view, a Python library that writes skill code, hands it to Virtuoso, has that evaluated to manipulate schematics, layouts, and the like. And that produced a lot of great research. We got a lot of good tape outs out of it. Is there a kind of a lag between what you guys see and what I'm saying?
Your page
Slide-wise?
is loading right now, so I'm not sure if that's internet issue.
I'll tell you what, let me reset this a sec. Okay, so time goes on, the circuits get bigger, the chips get bigger. Eventually, this is a theme in a lot of these projects. The generators start taking days or weeks to run. The group behind this realizes this sending skill code strings to Virtuoso gets really slow and makes a very fateful decision, which is SI2 offers a C++ API to the underlying data model called open access. If you're a member of SI2 and can get access to it. And so the project transitions to using this very directly and very comprehensively. Big problem ensues, which is that we then lose that license. It's been gone now the entirety of the time that I've been here, which is over 3 years now. And while it's not the only factor, it's a material factor in the fact that development of that project's really stopped here. Right. It's also been impacted by the fact that the sort of original designers, both amongst the grad student researchers and key professor, have all left. But an important fact is we can't write this. We can't even compile it, in fact. So we have a few users left, but with this gone, pretty much back to that prehistory, right? What are you back to now is kind of what everybody else does. So the first lesson of this, to me at least, is don't do that again, okay? Don't get stuck in this situation for some central building block. I should have added at the beginning, by the way, I encourage you to interrupt. I probably won't see the hand thing, so just interrupt me and talk and I'll answer questions midway through. So first question is, what is this thing that we got licensed out of? What is in these design databases, or at least this one in particular? And at bottom, this is a binary data format, and in OA's case, a C++ API to manipulate it. So do things like add a polygon to a layout, get all the instances in a schematic, some notion of linkages between these things. And the message here is they're not made of magic, right? This one does have a magic facet, which is that it is the format for the most popular analog design environment, but they're not in principle the hard part. And so I'm going to introduce one of our projects next, which is called VLSIR, or Design Databases Made for Protocol Buffers. So I'll introduce protobuf first. I know depending what audience I'm in, there's more or less familiarity with that project. The idea there, the goals there kind of start with the advent of the cloud hyperscaler companies. And so if you have tens of thousands of engineers, hundreds of projects, hundreds of kind of server-side programs that need to communicate with each other to do things like the largest web scale companies do now, most have reached an acknowledgement that there's just no practical way to get all of those engineers on the same page as far as what language we're going to use, what versions of all the libraries we're going to use, and the like. So the method instead is break these up and have some interchange of data that can readily get back and forth between them. So protobuf and a number of similar projects that are kind of offspring projects take a similar approach, which is you define data in a sort of data language. I think of this as if you can write a C program, but you can only define structs. That's it. and the struct type is called message, which is sort of indicative of it being designed for communication between these programs. But the gist of using this is you write this schema data model and then run this compiler that produces code in kind of any language you like every popular language that would use it, and then exchange between programs in those languages. All right, so this is an important motivating project. Captain Proto, flat and flex buffers are similar ones that are all share these traits I'm talking about here that I think are quite valuable to our problem. There's another project I'll introduce, and this is cited by a lot of IC industry projects of late. It's LLVM. And the particular component or particular facet to highlight is this breaking of that project into these three layers. So LLVM is the compiler infrastructure that's become very popular, most prominently powers the Apple Clang compiler. And one of the central ideas is this having this middle intermediate sort of interchange layer, which they call the LLVM IR, and splitting up the front and back ends, where front generally corresponds to kind of programming language and back corresponds to target execution environment. So the goal here is if you are going to change, say, the front end for Rust or the back end for x86, it doesn't necessarily screw with everything else, right? There is this modularity and this capacity to exchange this thing in the middle. So those two pictures in mind, our VLSIR system looks a little bit like each of them. There's a protobuf schema called VLSIR and a paired, the ideas that are captured in that data schema are circuits, layout, and kind of SPICE class analog simulation to date. The interchange, so that serves as the middle layer of something analogous to the prior picture. The interchange is on the front end. We use various, what we're labeled here as fancy front ends, so kind of nice programming interfaces to do stuff to this VLSIR data model. So we're going to look at several of these fancy front ends over the course of this presentation, but in these different programming languages that the protobuf compiler or compilers support, write code to manipulate circuits, manipulate layout, run and parse simulations and the like. And on the back end are really the industry standard formats. So many of the projects Mehdi cited in introduction, there's one key one called VLSIR tools, which is kind of the primary interface to SPICE simulation and net listing, and several layout centric projects that both know how to manipulate this content and get it in and out of industry standard formats like GDS and LEF. So there's a handful, this is all relatively new, but there's a handful of ongoing projects here. There's a Sky 130 SRAM compiler in the works that I know has gotten a good amount of attention by the community working in the open source technology. Similarly, researcher here, Ariaris Parsi, working on FPGA compiler. Those are both kind of structured digitally looking circuits, whereas the rest of this list is very analog. A couple of data conversion projects, both in continuous time sigma delta and ADC based. And then the last, which we'll look at in some more depth here, is the USB 2 PHY. So what's in these things? Again, I come back to this, it's not rocket science. This isn't the hard part of our job, is what is in this data. This is not exactly the VLSIR schema, but it is reflective of it. Right? This is not in protobuf syntax. In fact, it's in Python's. But what's in a layout at bottom is two things. One are geometric elements, shapes, 2D shapes that have a 3D layer affixed, and instances of other layouts. All right, so this left half page pretty well describes GDS and OA layout and many others. Circuits similarly have even less. If you think of structural circuits as being analogous to what's the content of a netlist, they include things like ports and signals, but mostly instances of other circuits and connections there between. All right. So this isn't the literal VLSIR schema, but really does convey the idea of what's behind it. Now, there's another type of thing in this big picture space that I want to introduce to motivate one of those front ends. And we'll get there through a little thought experiment, which is basically a test of how well we understand what these things are ourselves. And I call this a dinner party test. It's really how well could you describe what this thing is to someone not in your field? All right, so I'll do a couple of examples. If, let's say, I'm explaining to someone who's smart, but not an engineer, maybe they're a doctor or a lawyer, like, what is this thing on screen? I think I do that pretty effectively, right? It's kind of a list of instructions for the computer to do. It goes top to bottom, it does the first thing, it does the second thing. There are some special ones that say jump to here or jump to there or keep doing this. They probably largely get it. Second test, I also think I can explain pretty well. What's this? This is a blueprint. Right? This is the physical design. This is the physical fabrication instructions for a chunk of a chip. The X and Y axis are stuff to sort of shoot at a silicon wafer, and the colors are sort of Z-axis markers. Right? Different colors reflect sort of different depths in and out of the screen in this sort of 2.5D view. The one that I think is much harder, and in all honesty, on some level, I don't know what this is. Now, as a practitioner, I obviously do. Like I said, I come to this as an analog designer, and in some sense, my career is made of these things. But like as a person, I really am not sure I know what this is. And clearly, it's a schematic. But why these little squiggles have such significance to me and to everyone else in our field, I'm not sure that I can explain. And that's even for, this is a good schematic, right? We all can tell what this circuit is and does. If you've been out in the field, you've seen most real schematics, which don't tend to look like that. They tend to look a little more like this. Two giant rectangles with 500 pins in between them. If we zoom in on them, no one has ever been willing to name the instances in them except for the default value. Most of the signal names have about 5 underscores in between them that are essentially making hierarchical sub-references into one another. The circuit names themselves are, what are these examples? Top underscore core underscore all caps old underscore V3 and core underscore inner top V4 all caps Jim's version. That is not that much worse than actual circuits that are actually out there in the world. Better yet, we zoom in on some of the connections between these. They each have ports named who, what, when, where, and why. And there's a note. Now, this is actually better in a sense than a lot of industrial schematics. There at least is the note. But what the note says is internally, who connects to what and when, what connects to who, where connects to when where is high, what is disabled, and who reroutes to where, which is, kind of an Abbott and Costello routine mock comment, but is honestly not that much worse than a lot of real life ones. So I think there's a couple of reasons why we have so many of these just really bad ways of describing these circuits, of designing these circuits. There's no argument that this picture is like the best way of stating the content of this thing or designing it that I can see. The reason that they're there is because they're sort of entombed with other schematics that are better. And I think if we can break that up, we can do a lot better in this space. And that's kind of what motivates the first of those fancy front ends I'm going to show. It's a project called HDL21. This is an analog HDL based in Python. The goals here are, first and foremost, this is to be for circuit designers. This is a group of people who has a lot of specialized knowledge. We've talked in this meeting in the past about subthreshold slopes and how they impact certain classes of circuits. We'll talk about phase noise of oscillators later in this presentation. This is a group of people who has a lot of hard-won knowledge that it's easy to lose track of in a forum like this, but a lot of programming is not necessarily part of it. And even I would say usually not part of it. So the idea behind this library is to expose the ideas that the people with the requisite knowledge to make the circuits are comfortable with in the most comfortable programming environment. And I think Python is the best language for that, as commonly recognized as sort of the most accessible, and perhaps more importantly, the place where most of the other stuff they would want to do is going to happen. So data analysis is a great example. If you want to get into machine learning, it's sort of the hub for that. And so the idea of HDL21 is to really expose these ideas, these circuit level concepts, sort of open-ended in the language, except in a few places to impose some organization on what can be some very disorganized projects like that schematic we showed earlier. So what is in that space? Modules are very central element. Generators, which is a term we use here at Berkeley a lot, are a first-class term here and an important one. And then all of the other stuff that only the sort of analog tribe needs and uses. Interaction with spliced class simulation, process technologies are first-class things, and our pip installable Python packages, corners, all of the stuff that you need to perform the task of designing these circuits. So the first major idea, kind of the thing that HDL21 circuits are made of, in a sense, is its module. Module is hopefully feels comfortable as a term and what you're used to that term meaning. So the way you generally make these is stick a little module widget on top of a Python class definition and then declare its content, which generally consists of ports, signals, instances of other modules, connections there between. If you can, so that one of the goals, again, a central goal is require the sort of minimum fancy programming. And if you can wrap your head around, this is going to be kind of a container for those four things, you can program this kind of hardware.
Hey, Dan.
Go ahead.
Yeah, what do you mean by fancy programming?
So, great question. So I don't think the entry point can be descend from this class and override these 8 methods if you want to do X, and override these other 6 if you want to do Y, and require a lot of sort of software development ideas. Right. So I think that's been a shortcoming of some past projects, is kind of not meeting these people where they are. A lot of people, we're going to see just the role of like functions in this context very shortly. And even that is not a level that I'm presuming people care to program at. Right. So the very next slide includes the sort of right half of this slide is, if you want to produce hardware in kind of, let's call it MATLAB script context, right? Just running beginning to end. As long as you're comfortable making a variable here called B2 and sticking stuff onto it, you can make these modules.
Perfect. Thank you.
Yeah, very good question. And that actually lends quite well into our next topic. So the module is kind of I think of it as a struct. You can think of it as a Verilog module. You can think of it as the content of a schematic. The kind of the other really big picture thing is the generator. We use that term here at Berkeley to mean all kinds of different stuff. Here it is a proper noun, which means it is a function of some parameters that returns one of those modules. And that's it. If you're comfortable writing that, you can make generators. Now, it's not any function that can do that. There are some constraints on them. Generally, stick another little widget on top of a function definition is the mechanism. This does some helpful things in the background. And there are some constraints we'll see on the arguments to this thing, the parameters. But the important thing to note is the program is dictating the entire content of the circuit here. Right. So in our example, we create a module, we create an input, which has a parametric width. And then also parametrically, depending on arguments, dictate the content, right? If the parameters say to include the reset input in this example, include it. If they don't. So that can do things like swap in and out architectures of entire subsystems, or just do kind of simple numeric things like change the width of an array. Now, this is where we get to the parameters, or where we get to some of the forced organization. And well, this is not from a bag generator or even a circuit program. This is kind of reflective of, certainly among grad students, so I get to spend a lot of time with now, but also among attempts to program this kind of stuff, what things often look like. This is from a machine learning project. It's a C function that I believe has 21 arguments, many of which are parametric sized in and of themselves. It's static, so it has internal state. So don't do this is one of the next goals. And the generator parameters have a couple of mechanisms, or probably a half dozen things to point out about them to help avoid that. The first is they're organized as a type. So they have to get rolled into one thing. It gets another little decorator widget called a param class on it to make it so. The generators only work with something that is kind of aggregated up into a type like this. Second, they all are, at least at sort of definition time, this param thing, which includes a couple of important fields. One is a required data type. Those all get type checked at runtime. This is another often kind of hot debate here, are these strongly versus weakly typed languages. And Python is great for getting rolling. It also can sort of roll up to be a problem in bigger projects, and particularly not especially well documented bigger projects, to have this kind of free form types of everything. This library takes the approach of injecting type safety at runtime. So all of these parameters are strongly typed. They all have a required description, and if they are going to be optional, if they're going to take a default value, then they provide one. So they do a few more things. So they nest. The example at middle is probably worth pointing out first. It's a very common one. So pretty much all of the test benches we'll see later use a parameter type along these lines called PVT with 3 fields, PV and T, where one's a corner, one is a numeric thing we'll look at later, and the last is temperature. So here we've got a test bench at bottom for VCO, where it's got its set of parameters, and then the sort of simulation setup has its own. Using these generators looks a lot like using parametric Verilog modules. The general gist is we sort of call them twice. The last 2 lines on the slide are really what I'm pointing at there, which is sort of call them the first time to give the parameters, call them the second time to give connections. The latter is how connecting modules work. You sort of pass in signals to connect my name to their ports. So this looks very much both like the module concept we saw earlier and the sort of Verilog analogy there too. So I call this an analog HDL. There's not much, in all honesty, that has been specifically analog about it that I've shown yet. But one of the things that really make it so is this notion of what components does the system bring to the party? What are their primitive elements? So what do I mean by that? By analogy to a procedural programming language, if this is C, let's say, the programmer can define structured types. If this program is say running a sports league, there might be structures for league and team and player. And then somewhere at bottom, it gets to things like string, int, float, uint 64, that the programmer is not bringing to the party, right? The system is doing that. These are the primitive elements. And what are those? What is the set of those is kind of an important definitional facet for a project like this. And what they are is basically the Spice primitives. So basically the things, more or less the things that are built into Spice are what are also built into HDL21. So in this example, the designer can make, let's say, a PLL, which includes a charge pump, which includes an op amp. And the things that the system is bringing to the party are things like NMOS and resistor and capacitor. They're, in fact, very highly inspired by some of our Berkeley hosted, like, original SPICE documentation lists of the sort of built-in components. So these are things that are irreducible in analog simulation. And so these are generally the things that SPICE has the implementation of built in, are the primitives. The list of them, many of these QR code links, by the way, lead to the HCL21 GitHub repository. The list of them is on there comprehensively and excerpted here. There are a couple of other ideas amongst these primitive elements. One is there are sort of ideal and physical flavors. The former is more like what I said in being directly implemented by a simulator. The latter is more a target to be sort of expanded to a target technology. And we'll see some examples of that shortly. So if you want to get out of HCL21, you want to produce industry standard stuff. That's one of the central tasks. So net listing works through that picture I showed earlier of VLSIR as the sort of intermediate interchange, produces VLSIR protobuf, and then some of the VLSIR paired software can turn that into your favorite netlist formats, SPICE, various SPICE flavors, Spectre, and the like. So exporting to there is one common way that we sort of get these Python programs into the rest of chip world. Another one that you probably use more directly, and this is really one of the very helpful facets of programming the hardware in this language, is you also run simulations from it. So HCL21 includes kind of all of the SPICE test bench constructs, the analyses, DC, AC, TRAN, sweeps, Monte Carlos, and the like, measurements, include external files, all of the things that would usually go into a SPICE simulation in addition to the hardware elements. And that VLSIR layer includes drivers for some popular simulators, particularly Spectre, Zeiss, and GSPICE, to execute these, soak up the results, and return them back to the Python program. So this is, again, an example of similar means of defining these things. There's a little sim decorator widget that I affixed to a class called mySim, and then define the elements very much like what would go into a test bench schematic or a test bench netlist. There's one sort of special field here, which is called TB. That's the test bench module. You've seen some attempts at, let's say, automating, generating these simulations that are pretty structured and rigid and painful to my eye. Ours, I think, has worked quite well, which is that anything is a test bench. Any module can be a test bench if it meets this one sort of nested criteria left here, which is a SPICE test bench is a module that has exactly one port. It's exactly width 1, and we're going to hook it up to ground. So you can think of this sort of netlist layer as having a single node, 0. We hook it up to a circuit that gets provided here called TB. This is the one thing it takes to be a SPICE test bench in the system. A more realistic one, which has VSS as the port, and then some signals, a DUT module, and a voltage source. That's another one of our primitives, by the way, hooked up between them. So you bring all of the test bench content to the party as a module. PDKs are also Python modules. So there are a couple of these built in. The Skywater 130 open source PDK is one example. You can pip install Sky 130 HCL21 right now, just as you can pip install HCL21 and run the stuff on screen. The PDK, yeah.
Sorry for being the one asking questions. I'm just curious. So, does Skywater actually provide this a Python module as part of their PDK, or is this something that you as a user or a technology group have to go instantiate?
So the clearly they don't probably even know about this project. Okay, and certainly don't provide this stuff. The good news is there's not all that much to provide. So generally what these PDK packages include is a group of, we can think of as module headers. They're called external modules in the system. Other kind of comparable projects like Chisel, also here at Berkeley, call them black boxes. Think of it as the function header analog to the module. Right, so it's something like the port list, the parameter list and types, and these things on the screen, sky130_fd ... are those. So that's sort of part one. Part two is there's one PDK compile method for each of these packages. And the general gist of that is actually the next slide, which is take these generic primitive elements that we looked at earlier. So HTL21 provides all of these sort of process agnostic transistor, resistor, and the like. And each technology has a compile function that essentially maps them into their own types, their own devices. So the circuit I showed on the prior slide is called SkyInv. It sort of directly instantiates the PDK devices sky130_. The next slide makes the same thing, but does so by first creating these generic devices and then running this sky130.compile on them. So that's one of the important elements of kind of process independence. There's, I say this is kind of for the analog tribe. Some of what I mean by that is just in points of emphasis more than in kind of technology, right? And one sense in which I mean that is there are built-in notions of things like just the fact that there's going to be stuff outside that's not Python code that's necessary for interacting with these technologies. So each of these PDKs defines a thing called an installation. Usually it consists of, mostly it consists of things like file system paths, right? So something like where are transistor models? It might be where is some library of cells that comprise a standard cell library or some other cell library. And the other helpful paired facet is by convention, each kind of file system or site or server defines a module, short Python file by convention named site pdks.py. That sort of sets all these up, right? So create these install things for any PDKs that it wants to run. And the helpful thing about this is that it makes this separation such that we can distribute code that includes these simulations that has references to things like mypdk.install.models while getting them separate from the details of whoever's process is going to run them. All right, so you can discount this as a headache, but for I think most of these projects, kind of step one is download all the source code and start modifying it to reflect your file system stuff, your sort of computer's stuff. And I think that is in the way of a lot of very helpful things like being able to use the central package managers to distribute these things.
I have a question for you, Dan. Is this part of the Conda packages that we use right now for installing the tools and the open PDKs and all?
No, then there's no specific Conda builds. This is on pip. So both HTL21 itself, I'm sorry, it's on PyPy, so installable via pip. So both the HDL itself and the built-in PDK packages are both hosted on PyPy.
Thanks.
Several other important helpful features. One we've actually glimpsed at earlier is the sort of numeric type for a lot of the physical elements. It's not necessarily obvious that it's not a great idea to use floating point numbers for things like the physical dimensions of IC elements, but it isn't. And particularly because the floating point numbers are subject to floating point error. And the elements often have allowed and disallowed values. Think of like the length of a MOS transistor, right? Might have values that are 10 nanometers allowed, 16 nanometers allowed, 20 nanometers allowed. no other numbers in between are. And those, nowhere is it written that those need to fall on IEEE floating point values. So what we provide, and the primitives particularly rely on this, are these prefix numbers. The general gist is there is a decimal valued numeric part and an SI prefix. So micro, nano, femto, etc. Expose those as their sort of normal single character names. And then what I think makes it look very intuitive to use is this multiplication operator. 1 times mu means 1 micro, and 20 times n means 20 nano. So that's essential. That's especially useful for the primitive elements, sort of at the bottom of the hierarchy. Those are a lot of tools sort of up hierarchy, right? So we looked at that schematic earlier, which had tons of ports that were like sub block 1 underscore sub block 2 underscore sub block 3 underscore reset, right? And that kind of stuff happens a lot. You have signals that travel together. System Verilog introduced it, has an idea for this, which he calls interfaces. Another popular project here at Berkeley, Chisel, calls this idea bundle. What they all share are their structured connections. And you'll often hear from analog designers like, I don't do that. And they're wrong, they do it all the time. Very, very common example is a differential pair. So this one is popular and common enough that it's sort of built in. P and N are the 2 legs of the diff pair. And you can nest them, right? So quadrature is a thing that gets instantiated all over the file we'll look at, which is an in-phase differential pair and a quadrature phase differential pair. And you can create that bundle of signals very similarly to creating instances of modules, call them, and then can connect to the subparts. So here we have a diff amp on I and a diff amp on Q reaching into the .I and .Q. There's differential is kind of a special enough case that bundles can be defined arbitrarily and user-defined ones all over sort of large-scale circuits. Diff is common enough to be built in and has a paired facility called pair, which is 2 identical instances, right? So this is another thing that comes up all the time. The point of this slide is really the last 2 lines. A pair of some module or other instantiable thing makes 2 of them. Here we're making an NMOS resistive loaded amp, which the NMOS connection goes to, you'll note the input and output are both these differential bundles. And the load is probably the best way to point out that one side of that diff pair goes to the differential output, one pair goes to the scalar signal VDD. The general gist is if these things get hooked up to a diff pair, hook up P and N to the 2 legs of the pair, they get hooked up to a scalar signal, hook them up in parallel. That works for more than primitive elements. So a very popular circuit you'll see, including later in this talk, is a sort of pseudo differential oscillator stage with forward inverters and cross-coupled inverters, which have a certain ratio in strength. Creating those as a pair this is a literal module we'll use and see later. Lots of other stuff. So lots of the other niceties that you're kind of used to are built up, including arrays of instances. So this is sort of syntax built into Verilog, or this sort of angle bracket thing built into Virtuoso. I think an even more helpful realization here, and again, the point of the slide is really the last line, is that an instance of a module times an integer is a great way to create these things, right? So the last line is making 3 instances in an array of this child module at top. And kind of related to that is slicing and concatenating signals. So all the signals are sort of buses, they are all vector width. And there are facilities for concatenating them together into bigger ones and then slicing them apart with the built-in Python syntax, the square bracket operators, the sort of usual in-language idiom for doing so. This resistor ladder, which gets used as part of a DAC project, defines sort of top and bottom ports, a bunch of taps in between, and then concatenates them into this R units is, for Virtuoso users, very much like the sort of wraparound syntax with the comma separated concatenation, and then splitting out one of those to tie to a single capacitor at the end. Okay, so this is a good rundown of what's in HTL21, and I sort of motivated this with these very bad schematics, and hopefully it's come across that I think in general schematics are bad and they should probably be code. And you might be able to guess the next word is but there's still some really incredibly awesomely helpful ones. Like I said earlier, I can't on some level describe what this is, but on another level, I understand this picture so much better than the code version thereof, right? So this is a great example. Another great example of kind of wacky analog schematics. And these are all actually examples from the forum that brought this to mind, which is here at Berkeley, we give all of the grad students in circuits an exam where we give them kind of wacky circuits like this and have them explain how do they work or make another one similar to it. And it was really while helping the students this year prepare for that I realized, you know, at this kind of primitive level, it really is much more descriptive. It really does land a lot better, including with me, to describe this circuit this way. So we saw all of the good things about the HDL code earlier, and I'm going to tweak that prior statement to say most schematics, and I think most by quantity fall in the earlier ugly category, are bad, and most should be code. But there are some good ones. And so how do we get the good without the bad? This is a quite new set of work, and it kind of had been noodling around for quite a while. And then a few months ago, right around the time of that exam story, we also had our first son. So I had some idle time and had been thinking about this, about what would be a good mechanism for getting the goodness of those pictures, right? So criteria one to my eye is just easily get in and out of code, right? We've established the sort of code being a better paradigm for so many other layers of these circuits. Get in and out is central goal. Second, be shareable. Don't require, I actually had to re-stand up Virtuoso to draw those ugly schematics I showed you earlier. It took me like all morning to get through all of the various layers of software required to connect in. And we really shouldn't need that to convey something like that picture I showed a few moments ago, and make the good ones easy and bad ones hard, right? So I think the central realization is those schematics are two central things. One's are a circuit and the others are a picture. And that's really kind of the motivating insight behind the HTL21 schematic system. So we saw that circuits earlier, we looked at them in VLSIR, they can be these structured data types. So we looked at them as Python code. Can we get something in sort of easily renderable, easily visible pictorial form that also pairs with that kind of structure? And there's a format that is, I think, particularly well suited to that, which is SVG. SVG is scalable vector graphics. It is one of these sort of web systems central formats, along with HTML, JavaScript, WebAssembly. This is an XML format, so it's text looking like the stuff at bottom left that your browser knows how to turn into pixels on the screen, right? It knows to turn this rect into a rectangle at a particular location of your screen and the like. It's also structured, so it's XML data. It has semi-custom metadata and structure, which is what you can use to embed things like, say, a structural circuit. So the idea of HTL21 schematics, link at top right, is the schematics are SVG images. It's a single file. It is renderable by essentially any computer you can find if you didn't dig it up from more than, I don't know, 15 or so years ago. It does not rely on linking to some external database. at least to show you the schematic picture. So sites like GitHub can render them. Any web browser standing on its own can render them. Lots of other general purpose pieces of software can render them. If I email you one of them, you will be able to open it on its own as that file and look at it, which I think is a really important element. I think it's another counterintuitive facet that most of this stuff is read mostly. So even when writing, you are mostly reading. So what do these look like? This is a real life example. This is in fact the upfront example, this inverter. This is an SVG file that also contains the structure of that inverter. If I add the emoji for the mind blown emoji from OpenMoji, it remains a valid schematic. This still runs and simulates and does all of the same stuff. So how does it run and simulate and do all the same stuff is, part two, that is, these schematics are also, in a sense, graphical Python modules. So they run as HTML21 generators. And we'll see just how in this very next slide, which is when I said I wanted it to be as easy as possible to get them into code land. The easiest way I could imagine is they import directly as though they were Python modules. So the language has a nice facet that is its import keyword or its include external stuff keyword is in a sense overridable. And the system includes a relatively simple mechanism for given a file named inverter.sch.svg, import inverter gives you that schematic as a generator. So there's a demo repository linked at bottom. It is an only slightly more complicated and useful example than this, where we import from a schematic and start instantiating an HDL code. What does the sort of thing that gets imported look like is a relatively straightforward, I think, mapping into the stuff we saw earlier, right? So each instance of a primitive element, just call it an element, turns into an instance in the generated module. The ports turn into HDL21 ports, the wires turn into signals, and you get something very much like what we were describing earlier. So sort of inverting. Go ahead.
No, I'm sorry, Dan. Just say your QR codes work great, by the way. I've been trying them out here.
Oh, great. That's good to hear. So yes, that kind of big picture insight that, this is a circuit and a picture. We invert this in some sense. It's a picture first with a circuit embedded within it. And more specifically, it's an SVG file that runs as a graphical Python module. Okay. So the pieces of this, there's kind of two halves in a sense, split up by this SVG format and schema we layer atop it. There's probably most of the work is on the kind of GUI side, which is all in WebStack stuff. There are a couple of ways you can run that. We'll see shortly these editor platforms. And then there's a very short, a very concise mechanism for turning this into executable Python code. So the ways to interact graphically with these schematic pictures. First, there's a dedicated application. So this uses all of the web stuff, which has made it very, very fast to bring up, right? It's really just been me working on this very recently. And getting to the phase it's at in that short amount of time has been a real asset of having that web stack. Now, for a lot of EDA stuff, you'd say, well, that's definitely going to be way too slow. But this brings in another important trait about schematics, which is they really can't get that big, or at least they can't get that big and be useful. So you're never going to have a 1,000,000 element schematic, at least useful one. You're probably never even going to have a 1,000 element one. 100, maybe even pushing it. So having that kind of software stack behind these, I think, is pretty reasonable. And then the sort of motivating use case for how to interact with these, given that they are essentially graphical pieces of code, is to inject them into your favorite code's IDE. So that is the other primary mechanism, which is a VS Code extension. So that's become sort of the most popular IDE over the last few years, and is relatively straightforward to map something like that GUI application into an extension that runs when you click on a .sch.svg file, you get the GUI to manipulate this bipolar circuit. You also get some nice things that kind of like, I don't know, there's some level of kind of built-in abuse to working in this field, I think, that you just don't realize you can get stuff that was invented after like 1990. Like, for example, when your computer goes into dark mode, your schematics can go with it and right back into light mode along with it. And that's another part of the premise of bringing this into this kind of more modern era set of stuff. So I described that these are kind of graphical code, and there's an important element, there are a couple of important facets of how that works. First is kind of, how does it know what to refer to? How does it know what these transistors and resistors and the like are? And the general gist is that there is a sort of code section to each of these schematics. We call it the code prelude because the idea is that it sort of runs before the pictorial part. Generally, the code preludes do three things. They can't do anything. They get executed as any other Python code. But usually they do three things. One is import the stuff the schematic's going to use. So import stuff from HCL21 primitives. Two is define the parameters, not shown here. But three, and this is a feature that I've always wished exists in schematics, and it's very straightforward to roll in here, is just define reused things, define variables that get reused through the circuit. So if you think of this code running first, it defines this p-bias thing, which is a sized transistor, sort of parameters applied transistor. P cascode is a different size, it's much smaller, common tactic, and R bias is similarly sized. And then the identifiers on the schematic elements really refer to those identifiers. Right? So this is sort of a way to say, well, this thing changes, both of these two transistors change with it. That is pretty central to how this works as a single image file, or something related to that idea is essentially how this works as a single image file, which is really this division of how these schematics figure out what their content, how does HCL21 ultimately figure out what the content of the schematic is. So this is different from other systems I'm familiar with, in that the picture part, the elements, the circuit elements, this picture representing an NMOS transistor or that representing a NPN or PNP, really just bring two things to the definition. One is the picture itself, what it looks like. Two is the port list. And this, what we call of string here, this thing that says NMOS parentheses, is really what dictates what it's going to end up being in a netlist, in an HDL generator, and the like. So that can be any of the stuff we looked at earlier, right? It can be from a specific technology. It can be the built-in generic primitives. They can get compiled after the fact to a specific technology. As long as they match that port list, they work. So one sort of easy example of this is you generally have in almost any other such system I can name elements called like current controlled current source and voltage controlled current source, similar families. And here there's just a thing called iSource4, right? So if you want it to be voltage controlled, type in VCCS, and you want to be controlled, type in CCCS. And that's really how this kind of linkage works. This no attached sort of entombed in database, it really sort of links through these code identifiers. Where do these live is essentially at the bottom of the hierarchy, instantiating things that are similar, not identical to, but analogous to the HCL21 primitive library. Transistors, resistors, passives, inductor, and the like are examples we've seen. And that's very much part and parcel with one of the goals I said earlier, which is make the good schematics easy to make and make the bad ones hard, right? The 500 pin 2 rectangles should be code instead. And this makes it so that you can draw the good ones instead. Okay, so I know we're past 10. I'm sure folks have to go. I think, reasonably pause here. What do you guys want to do?
Yeah, Dan, I didn't really want to stop you since this is really exciting. But maybe we can reconvene for another meeting to finish your talk. What do you think?
I think if this sort of general consensus is roll another, I don't know, 15 minutes or so, I can very quickly show what's going on with the USB fly. And if we'd rather do that separately, that's fine.
What do you guys think? Anyone? Do you guys have any opinion on this? Or strong opinion?
I'm happy to keep rolling.
Cool. Let's go. Andrew?
Oh, I was just going to say, will Dan be able to distribute slides and we can email him, or does it have to go through this group's reflector? What I have, all sorts of exciting thoughts and questions.
Yep. I actually left out, I have my one and only speaker note was actually kind of for you and some similarly situated academic projects, come to think of it. Particularly with the HDL being based in Python. So I'm just gonna keep going. People will drop off, we'll have the recording. And
We could
short
do
answer
the
is,
Q&A next time.
yeah. Short answer is yes, I will distribute the slides.
Great, thank you. I chatted with Mehdi about some questions and he can ask them or not. But thanks a lot, Dan.
Yeah, thanks. Is our slides coming through again?
Yep.
So I think going back to our HDL and particularly stuff, like this, I think there's an untapped opportunity here, untapped by us to date, which is a potentially good point of interaction with some of the other projects we've looked at here, which is we have a lot of kind of not quite analog synthesis, but analog layout automation projects that either need or try to infer a bunch of facets of intent about the circuit, right? So things like which instances are differential, which are intended to be matched, which signals are really important and the like, are things that, we've seen projects that have to write whole piles of software in order to infer. And here we've got a real opportunity to just have the designers tell it, right? We have this sort of open-ended space to say, both in sort of additional structure about what's a pair or what's an array or whatever, we also have sort of open-ended places to affix these things to the HDL objects directly. So if that's, I think that's potentially helpful as a pairing with some of the some of the other projects here.
Dan, I agree with that. So in OpenFA we have a lot of description in Verilog, right? And I think in your framework, it might be useful to try and see how we can reuse that. We don't go too much in details, right? Like it's not a transistor level; it's more of an auxiliary cell, which is much it's more like a standard cell level. So I think it's great to try this, and there's also another opportunity here to discuss about integrating this within OpenDB. I don't know what database you're using, but we had the initial discussion about including some of this in the database from OpenRoad, and that would make it really, really useful, at least to OpenFA. Not sure about others.
Well, it might be worth rewinding to an earlier section that was all about the VLSIR design database.
Yep.
But certainly happy to chat about all the above.
Sure.
Okay. Very short section layout. I said earlier we would run out of time. We ran out of time even faster than I expected. Really, layout's going to be maybe next time. I have lots of thoughts about programming layout. What I'll do for now is just flash a few links to first that VLSIR format itself, defined in Google's protocol buffers. Layout 21 is a set of Rust libraries for manipulating that and related different layers of layout sort of models, including the ones at bottom, which are sort of get in and out of the industry standard formats. I think that language is a very powerful tool, especially for projects that have a need to sort of be embedded in other ones. This is, if you're not familiar with it, you think of it as kind of modern C replacement that can be embedded very directly in either your C code or any of your scripting language code and runs at native speed. So we can talk about layout in another session. What I'll briefly go through instead is work on this USB-Fi. The motivation and goals for doing this were twofold. One is, as kind of a more elaborate than the things I showed earlier, demo case for all the software, but also making something useful for this community, right? I think it's been really beneficial that we've had all of this attention and energy in Sky 130, and we thought, well, what is a practical project in that space? And in 130 nanometer, that technology came out in something like the 20 years ago range, 2002. We've got a group here that has a lot of serial link expertise and background. That's where a lot of my work has been. And we've also seen a need for stuff in this open hardware space to be able to talk to, host PC. Like having one of these USB links would prove very helpful to a lot of the projects I've seen come through that pipeline. So the generation that came out around that time is what's called version 2.0. It runs just under half a gigabit at 480 megabit. And that's what we've been making. So what that looks like as far as kind of block diagram getting back to processor or processor-based system is, if you think of starting at kind of compute at left, there will generally be some bus actually being very popular, tie-link here, talking to a block generally referred to as a USB controller. And helpfully, this generation of that interface also defines a standard controller to PHY interface. In fact, there are two flavors of it called UTMI and ULPI that are generically for intra-silicon IP and discrete chips, respectively. And what we're making is the box at right, and slightly more specifically, kind of building it right to left. So that includes digital analog subsystems. PHY analog will have PLL, CDR, all of current drivers, all of the sort of custom stuff, and then a thing that sort of turns this UTMI and ULPI back and forth between what these analog circuits need. All right, so think of this as being built, start at the cable or USB connector back. For a very broad, I'll assume a very broad kind of SerDes knowledge, which is to say in designing these, there's kind of two recurring central problems. We'll call them the equalization problem and the clock recovery problem here. There are means to address them on both sides of the link, but they kind of manifest largely at the receiver. The first one is any channel you send serial data through tends to have loss and have that loss be frequency dependent. Right, so that matters because higher transition density bits have more high frequency content, more longer runs have less high frequency content. And just fact about these modern SerDes that I think anyone not very close to them probably wouldn't realize is we use this eye diagram to sort of characterize the state of the link at any given point. And generally it looks something like the picture I left at the TX. And even in TRA, an embedded system, you often get a closed eye like the thing at right. In fact, you generally do get no eye at the receiver, even just running through sort of PCB traces and intra-system things. So there is a helpful fact about this, which is this is deterministic and recoverable. Equalization is generally the idea of we're going to invert that frequency dependent loss of the channel and sort of apply the inverse transfer function at the receiver or at the transmitter or some combination thereof. Big problem two is clock recovery. One of the general goals of making SerDes is send less wires, send less pins, send less stuff, send more data for less hardware. A particularly painful thing to send, particularly over things that run along cables and all over, a car or your home, is a clock. So many don't, right? Many do what's called embedded clock, where there's no explicit clock sent from transmitter to receiver. The receiver is to recover essentially a surrogate transmitter clock from the data transitions. We refer to that general problem as clock and data recovery. Each have their own sort of frequency reference, crystal or similar, but getting this receiver to take incoming data stream and turn it into good sampling instances to essentially create a replica TX clock is one of the central problems. So USB 2 is a little older. If you go through stuff in the intervening period, you see a lot of a circuit a lot like this. I would be very sure that there are like several dozen of something like this circuit in between the camera in front of me and the monitor in front of you, in which equalization is some combination of continuous time, and this feedback-based thing generally makes it DFE. And clock recovery starts by making a multi-phase clock at something close to the TX rate, and then doing this phase interpolating sort of muxing between finer phases to find an ideal sampling edge. This has worked in a ton of places. It's been very effective scheme. One problem applying this to USB, and we honestly started off making something very much like this, is this loop there is a feedback loop in producing that recovered clock. And it does take some time to settle. There's generally some sort of link or protocol level setup to say you get this many bits where we ensure transitions, with sort of tiers of how many there are going to be and how often there have been between them. And USB 2 turns out to have a pretty difficult version of that problem, which is it essentially says we will start transmitting and you will start receiving within 8 UI with no prior notice. Now, in contrast, it has a very easy version of the equalization problem. And so our high-speed PHY looks more like this, which is there's no dedicated EQ, but we do have some, I think, relative innovation on the clock recovery front, which is it uses injection locking. So primarily for the CDR, primarily to do this almost immediate term syncing to incoming data edges, we then apply that same injection locking to the TX PLL. So there's one central goal here is there's a very small fraction of what like an industrial team would have to produce such a piece of IP. So minimizing the amount of stuff is a really central goal, and actually getting that sort of phase interpolator system to the point where it can do these, what we generally call burst mode CDR things, where it can wake up in just a few UI, requires quite a bit more hardware. So what we've got is focusing on the receiver. There's a sort of frequency locked, injection locked VCO, and a sort of data transition pulse generator locking it onto edges and incoming data. The TX PLL is more or less the same circuit, just with those edges coming from the ref clock. If you don't know injection locking, the idea is there's some spinning oscillator, and think of it having some little reset switch into it that the sort of input clock tells it, okay, go back to phase 0 right now. That is all descriptive of kind of the 480 megabit stuff. USB has this other unfortunate lineage that it has to kind of walk up its old generations, many of which are higher voltage. That does inject some complications to the higher speed stuff, particularly about sort of voltage compliance and devices that get used. But it also requires a bunch of these other sort of surrogate circuits for what it calls full speed 12 megabit mode, for sorting out what state you should be in, and all of those things at bottom right. So this is in progress. This will be, I expect, early next year, one of the shuttles. And it's all in the stuff I showed earlier. So using the things I showed over the first part of this presentation, this is a very, very lightly massaged version of that analog phi top level. And, maybe you have to squint a little bit, but fits in two columns of not a ton of stuff. And a lot of the reason it can be so is that it can have this structure about things like what are these bundles of signals routing to each other, and how do these things all kind of connect into something like this block diagram. And moreover, where it lives, where it runs, where I use it is all in Python land, right? Which is very helpful in that it's the same place that a lot of similarly situated folks want to do things like data analysis and figuring out how should we resize the circuit and what is going to be enough coverage over some frequency range. So test bench at left, relatively simple one for one of the preamps that gets simulated, results get pulled back in, or get spat out to something like at bottom right, we've got an injection sort of locking simulation in industry standard interactive waveform viewer. But many of the rest of the pictures are kind of all in Python, or using the sort of very popular suite of visualization and data analysis libraries, including for the single transistor simulation at bottom left or bottom middle, looking at these kind of sizing and GM over ID parameters. So we'll have more to share on sort of parametrics and performance and the like of the phi as that gets closer. It's in progress, like I said. And I hope that it's going to be, I think it can be helpful. I would point to really all of the things I've talked about in this talk are really welcome for contribution. One particular element I would highlight in conjunction with this phi is, we're building right to left. I fully expect to be able to build the analog part in short order. The phi digital will be kind of after that, and we may build a test chip before we get to that. The controller is outside the scope to date, and if there are contributors if there are folks who are interested, it could be a great pairing. Because like I said, we've got some folks who have this kind of knowledge on the right that I don't think is very easy to find in this community. And so, work kind of further to the left of this picture, or pairing of other work, of related work further to the left of this picture, go a long way. Okay, I did 20 instead of 15.
Okay, great, Dan. Thanks so much for your talk. Is there any questions?
Yeah, I probably have a couple of questions. Not sure if we have time.
Yeah, go ahead, Sally.
Personally, I do. If you want to end the recording or call at any time, that's fine too, but I can answer anything. Great, thanks. So I was just thinking about the backward compatibility of HDL21 from the SPICE netlist to the SVG file, because that is actually a problem which I've been facing a lot with, Xscheme doesn't support it, and there is this Python library called skimdraw, which actually helps you to describe the circuit using all the stuff kind of similar to what HDL21 does, but it only exports the SVG file. It doesn't run any simulators. So I was just wondering if HDL21 has any backward compatibility, like importing the SPICE netlist basically to get the schematic out, probably an SVG file. Well, so I think there's a couple of categories there, right? So one is, can you sort of parse and input existing netlists? And we have a bunch of parsing, and actually another library I didn't show here. And we have all the stuff I showed, and there is a little bit of linkage in between them that would need to be developed. So conceptually, it's not very far off, but no, it's not a use case that we actively do. What we do much more often is you have an external net list and you provide one of these module headers, one of these external modules, which sort of declares the IO to the modules and instantiate that. So part two is the interaction with schematics, and I am familiar with the schematic draw library. That is a sort of procedural program that says, like, draw a line from coordinate 100, 120 to 200, 240 and the like.
Right.
Which is not something that any of the software I've shown here does nor will do. The way you interact with schematics is via GUI, the way you create them, I should say. And the way that you create HDL code is by writing code. And they do have these two different interaction mechanisms on purpose. Because I think those are the sort of the intuitive mechanisms for interacting with those two sort of modes. Now, could you infer schematics? Like, could you take an existing net list and try to infer, like, what's a good picture of it and produce it in this SVG format? Absolutely. There are many projects that do so. Many popular schematic editors have them built in. You can debate their quality, but they at least try. I've seen a machine learning driven one in a recent conference publication. And our schema and format is open source, and I think is quite straightforward at that. So I think it's a pretty natural target for such things. Would also be new work and would be welcome.
Understood. Thanks. Do you have any Jupyter notebooks to share? For us to try the HDL2 one, because I believe everything is in Python, so we should be able to get the SVG files at least in the end, right? By defining the hierarchy of a circuit.
Yeah, so again, there won't be any inference of circuit pictures from HDL code. And as far as running in Jupyter, HDL, probably you run it in anywhere you can run any Python interpreter, right? You can pip install and import it in Jupyter or anywhere else. There's a small library of built-in examples that are, kind of one screen length programs that, create a hopefully both simple enough and useful enough circuit. Many of them were actually the basis of the slides I showed here. So we can link to that more directly. Most of the development is in, code directly, not in Notebook, but it'll run in your Notebook all the same.
Understood.
Right. Dan, I have a question from Andrew. He was asking about SRAM 22. I didn't catch that, honestly. So I don't know if you have any comments on that.
There's ongoing work by another grad student researcher here to produce a Skywater SRAM compiler, more of this in the spirit of the commercial ones, both as far as the content of its output and the sort of parameter space that goes in. Is a gentleman named Rahul Kumar. I know he's gotten lots and lots of interest about that, as that's been a pretty consistent problem for many participants or would-be participants in the open source shuttles. That is, we can check on just how public that is. It's certainly not finished. It's certainly in progress, but I think has been going quite well, and I hope will be quite helpful.
Sure. It would be great to maybe, I'm not sure how open he is to give a talk, but to just learn more about his project. The other question I had is your OpenFi, is it available on GitHub, like the work in progress? Can we check it, or?
Yes, I believe that is one of the links I left out here, but it is.
Cool. All right. Hopefully you can share your slides. I can pick that up again.
Yep.
Any other questions?
This was a great talk, Dan. Thank you so much.
Yep.
Great.
And I will share the video of this that's been recorded today later this week. And also, Dan, when the slides are available, that would be great too. And just as another point is we are building a new CHIPS website that will be Hugo based and hopefully will enable easier contribution by different members in the community than what we currently have. So hopefully that will help aid productivity for all.
Great.
Great.
All right.
Okay, thanks a lot, everyone.
All right, thank you again.
Yep. Thanks, everyone. Thanks, Dan.
Yeah, take care.
Have a good day. Bye-bye.
Bye.
Thanks, Dan.
Thanks.